Hi, my name is Brookite. Welcome to today's video about the chemical element titanium. This is a picture of the element titanium. It has the atomic number 22. It was discovered in 1791 by William Gregor in Cornwall, Great Britain, and it is named after the Titans of the Greek mythology. There are 5 isotopes in nature. The most abundant is isotope 48 with 74%. And there are radioactive isotopes like titanium-44 with a half-life of 60 years. This is a picture of the nucleosynthesis of the origin of the chemical elements. Titanium is here. It is produced in exploding massive stars and exploding white dwarfs. Titanium, there are no known biological functions of this chemical element. This is a picture of the abundance of the chemical elements in Earth's crust. Titanium is here. It is number 9, very abundant with 0.63% Earth's crust. Titanium was also found in meteorites and the sun and in M stars. M stars are the most common type of stars. They're also called red dwarfs. They make about 75% of all the stars in the universe, and they contain titanium-2. These are a few examples of titanium minerals. At the left, that's Brookite, which is titanium dioxide from Karan, Pakistan. In the middle, that's Ilmenite, which is iron titanium oxide from Mont Saint-Hilaire from Canada. And at the right, that's Rutile, which is also titanium dioxide from Minas Gerais in Brazil. These are a few properties of the element titanium. Its density is 4.5 grams per cubic centimeter. For comparison, aluminium is 2.7 grams per cubic centimeter. Melting point is quite high with 1668 degrees Celsius. It is ductile and has a high tensile strength. With titanium, you can get a passivation with titanium dioxide. There's a number called Pilling-Bedworth ratio. That's the volume ratio of the oxide to the metal. And for titanium, this number is 1.77. For comparison, aluminium is 1.28. You can check my aluminium video if you are interested in how this works. The point is, if this number is between 1 and 2, then you get a good passivation layer, because the oxide layer will be like a layer of paint, and it will protect the metal underneath from further oxidation. However, this effect has a limit in temperature and pressure. This is a picture of anodized titanium, and this is a defined oxide layer. You can use this effect to give this metal color. This is a light reflection effect. There are no pigments involved. You can see you can make almost every color: gold, purple, dark blue, light blue, yellow, orange, green. But you can't make red. This is how you can make titanium. First process was the Hunter process from 1910. It's a reduction at 1000 degrees Celsius of titanium tetrachloride with sodium. Then you get 4 sodium chloride plus titanium. In 1993, this process was replaced by the Kroll process, which works at a lower temperature at 800 to 850 degrees Celsius. You get this titanium sponge. That's by titanium tetrachloride plus 2 magnesium. You get 2 magnesium chloride plus titanium. And you can purify it by leaching or vacuum distillation. However, this is a very energy intensive process, and that's why titanium is quite expensive. At the bottom you can see the price. For several years it was between $4 and $6 per kilogram. Then it went up to about $8. Maximum was about $19. And then it came back to about $11 per kilogram. World production in 2021 was 210,000 tons. Number 1 producer is China. This is the Van Arkel-de Boer process to make this is a process to make pure titanium, or you can use this process for zinc, zirconium, hafnium, or vanadium. This is called a transport reaction. You make use of a reversible reaction to purify the metal. At the left, this is the apparatus. Number 2, this is the molybdenum electrode. Number 5 is the tungsten wire. The raw material is put here at number 4. Then you use this reaction of titanium with iodine at 600 degrees Celsius to get titanium tetraiodide. This can then use the decay at 1200 degrees Celsius to titanium, and you get back the iodine. So the pure titanium will end here. At the right, this is the process, how it works. Iodine goes to gas phase and then reacts with the metal, transports the metal to the tungsten wire, and then you get back your iodine. These are the applications of the element titanium. At the left, you can see aircraft part. It is also used for alloys, for example, steel, for tennis rackets, golf clubs, spectacle frames, engine parts for springs, tools, jewelry, orthopedic implants, surgical instruments, body armor, propellers, and laptops. This is a nice picture of a big airplane, a Boeing 787 Dreamliner. It contains 50% composite materials, 20% aluminum, 15% titanium, 10% steel, and 5% other materials. And the titanium is within the elements of the engines and fasteners. This is a picture of titanium dioxide, TiO2. It is also called pigment white 6. It is used for paint and sunscreen, food coloring, toothpaste, papers, and plastics. It is, as a compound, not toxic. However, the dust and nanoparticles could be carcinogenic. This is titania. This synthetic titanium dioxide gemstone has more fire than diamond. Fire means sparkle in light, but it is much softer than diamond. This is a picture of nanotubes of titanium dioxide. They have a size of about 150 nanometers, and they have a big potential for batteries, memristors, catalysts, and capacitors. This is how you can detect titanium. You heat a sample with concentrated sulfuric acid, and then you pour it into an ice bath, which contains hydrogen peroxide. And if there's titanium in the sample, then you will get this orange aqua complex ion. This is the compound titanium tetrachloride, TiCl4. It is a colorless or yellow liquid. It is important for the production of titanium and titanium dioxide. You can use it for smoke screens, and it is important in the organic synthesis. This is the compound titanium nitride, TiN. It is a hard ceramic compound. You can make of the physical vapor deposition both steels and alloys with this compound. Typical thickness is less than 5 micrometers, and at the bottom you can see an example. There's a coated drill. It's coated with titanium nitride. This at the left is the compound perovskite. Perovskite has two meanings. One is this compound calcium titanium oxide. It was discovered by Gustavus Rose in Russia in 1839. And perovskite is also the name of the group of compounds ABX3. That's the general formula. And these compounds have a big potential for solar cells. In this picture, you can see two of the possible applications. At the left, that's the thin film solar cell with perovskite. They have an efficiency of about maximum 24%. And at the right, that's a tandem solar cell. It has a perovskite layer and a silicon layer. And in this tandem solar cell, you can get a higher efficiency than 33%. Perovskites have disadvantages compared to silicon. They are more sensitive to moisture and UV light, higher temperatures, and there's still active research going on in this field. This is a picture of rutile, which is titanium dioxide on quartz. This is from Minas Gerais in Brazil. This is rutile titanium dioxide from Skardu in Pakistan. This is mineral neptunite, which is potassium, sodium, lithium, iron, manganese, titanium silicate from USA. And this is a very beautiful microscope photo of titanium dioxide nanoparticles in a solution on stainless steel. This almost looks like art, very beautiful. And that was today's video about the chemical element titanium. Thank you very much for watching. Have a nice day. Bye bye.